All right, welcome to our fifth and final video solution for quiz 3. So here we're going to set up a line integral, which is supposed to return the length of the top half of an ellipse given by, okay, it's centered at the origin, blah, blah, blah. And then we want to convert this line integral into a single variable integral. Okay, fine. So first thing we're going to have to do is parameterize this thing. So we want an ellipse. So if that's our C, let's see, it's centered at the origin, so we don't have to start with any 0 plus or anything. The x radius is 1, so I can just write cosine of t. And let's see, the y radius is 2, so I get 2 sine of t. Now we just want the top half of it. So again, let me just draw a little picture. It's not a terribly great ellipse, but okay, I just want this top half. So I can start at 0 and I only have to go until I get to pi. Now this doesn't tell you which direction it's going, but remember the goal is just to find the length of this curve. And the length of the curve doesn't really know, right, which direction you went on it. So I can go in any direction I like, and I'm going to take the usual direction. So we'll let t go between 0 and pi. So I want to set up a line integral to get the length. So the length of c is going to be the line integral over c of, well, what? What's the function? What's going to go in here? Well, remember what this integral is doing. You're taking a curve, whatever the curve is, and you're chopping it up into little pieces. Okay? They look like they're not so little here, but you have to imagine they've gotten infinitesimally small. You sample the function, right? You sample the function at points in all these intervals, and then multiply that value by ds. And then you add those all up. Okay, I'm multiplying by this ds, which was the little arc length. But all I want is the length of this entire curve. So if I just added up these lengths, I would get the curve. I don't want to multiply by a function, but I could multiply by 1. So whenever we're trying to compute the arc length, we just use the constant function 1. Then all we're doing is adding up these little arc lengths, and we get the original curve. Okay, so we can translate this now into a single variable integral. The curve C was parameterized, let's see, t went from 0 to pi. The function 1 just has to be evaluated on the curve, but it's always just 1. I don't have to write anything down. So the next thing is the ds. So we saw last video, the ds was going to be the square root of x prime of t squared plus y prime of t squared. Okay, there we actually had a third one, a z prime of t squared, but there's only 2 here. Okay, and where do the x and y come from? Well, they come from the parameterization, right? We're looking on the curve itself. Okay, so if I take the derivative of cosine, I get negative sine, and then I square it. Okay, I get sine squared. So I have the square root of sine squared of t plus, okay, now I'm going to take a derivative of, it looks like 2 sine of t. Derivative will be 2 cosine of t, and when I square it, I'll get 4 cosine squared t. And then, of course, there's a missing dt here, right? Rule of 2. D's always come in these pairs. Okay. Now, I have this written as an integral, single variable, right, just in terms of t. What do I do next? Ah, yes, I do not compute it. Now, unlike last time where the integral we ended up with was dead simple, this one is not so easy. This one's not so easy because you're not going to find an elementary antiderivative for this function. This is a special type of integral. It's called an elliptic integral. Maybe you can guess why. So this is actually where we have to stop. If we wanted to compute this, we're going to have to use some numerical method, right? There's not going to be a nice elementary way of getting the value here.